experiments and FDS simulation on the makeup air influence on low power fires within an ATRIUM will be presented by Dr. Gutiérrez-Montes. He is assistant professor in the area of fluid mechanics, Department of Mechanical Engineering and Mining at the University of Jaén, Spain. He obtained his PhD at the University of Jaén in 2009, so congratulations, just recently. And his research focuses on experimental and numerical study of fires in large enclosures. Okay.
I would like to inform the speaker that the time for the presentation is 15 minutes. In order to control the time for presentation, a green card will be kept on the table, indicating that you are in time. When there are 2 minutes remaining, a yellow card will be placed on the table. The placing of a red card means that the time has ended, so you should finish the presentation immediately.
Okay. So, here we go. Well, I will present the results on the makeup air influence in low power hours within ATRIUM, which has been conducted by researchers of the University of Jaén together with the Universidad Politécnica de Cartagena. Well, fire and smoke control and detection are quite difficult tasks within ATRIUM, basically because there highly decreases the effectiveness of automatic sprinklers and smoke detectors, and the lack of floor-to-floor separation allow the fire and smoke to travel large vertical distances, affecting multiple floors at the same time. Well, at this point, one of the most commonly used systems to control smoke spreading are the mechanical exhaust systems, for which makeup air has to be supplied in order to conserve mass. This makeup air has to fulfill some goals such as uncontaminated outdoor air, to be supplied below the smoke layer, at a volumetric rate lower than the smoke rate, or, for example, at relative low velocities, not to disturb the flame or plume. Well, normally, at this point, maximum velocities of 1 meter per second are found in standards and codes. However, these restrictions can be modified if they are supported by engineering analysis. Maybe it can be conducted by means of experiments or CFD modeling. These CFD models are widely being used for this kind of engineering analysis, although there is a necessity of conducting more validation studies in order to check the capability of these codes for this kind of analysis. Well, in order to contribute to this necessity, here we're presenting the results from full-scale fire ATRIUM test, which have been conducted at the ATRIUM fire of the Centro Tecnológico del Metal of Murcia. This facility basically consists of a prismatic structure of 20 by 20 by 20 meters, which walls and roofs are made of 6 mm thick steel sheets, the ground of concrete. This facility contains vents, non-symmetrical arranged at the lower parts of the walls, which can be completely or partially closed. And finally, there are 4 exhaust fans at the roof with a nominal flow rate of 4 cubic meters per second, more or less. Well, in order to register the fire glass conditions, up to 61 sensors have been distributed in 4 different regions. Mainly, here we can see the main sensors used for this work. Mainly in wall A and C, walls A and C, the front and back walls, respectively. The smoke temperature has been measured 30 centimeters inside the facility at 3 different heights, 5, 10 and 15 meters, as well as the makeup air velocity and temperature at the central part of each vent. In addition, the smoke temperature has been also measured in a central vertical section parallel to walls A and C at 3 different heights, 5, 9 and 13 meters respectively, including measurements at the central line as a deleted room. And finally, the roof and smoke exhaust temperature of the fans have been also measured. In addition, a digital camera was used to take pictures of the flame, and the meteorological, the weather conditions were also measured. Well, here we're presenting results from 3 different tests for which the burning flow has been always heptane, containing a circular pool fire, 0.92 meters diameter, and placed at the center of the facility. The main properties of heptane, as well as the heat release rate curve as function of time of one of these tests, can be shown below. Regarding the venting conditions, the fans were activated for all the tests, and regarding the makeup air conditions for the first test, the 8 vents were completely open with no symmetric layout, and total inlet area of 97.5 square meters. For the second test, the vents were completely open but with symmetric layout. Therefore, only the 2 vents of wall C and the 2 vents closest to the corners of wall A were open. And for the third test, the same vents as in the second test were partially open at the 22% of the inlet area, with total inlet area of 10.83 square meters. Summary of the ambient and laboratory conditions of this test is shown in the table below. Well, once the experiments were conducted, the CFD code FDS version 4 was used to simulate these experiments in order to check its capability to properly predict the fire conditions. Well, it's worth highlighting that the turbulence has been taken into account by means of a large-scale simulation approach. The radiation model implemented in FDS has been used, varying the solid angle between 100 and 300 without any noticeable improvement, and a relative fraction equal to 0.75 has been set for the heptane. And finally, regarding the combustion model, the mixture fraction model is appropriate for a simulation of this kind of turbulent diffusion flames with fast chemistry. Well, now regarding the boundary conditions, the walls and roof has been modeled as 6mm thick steel sheets externally exposed to a quiet atmosphere at ambient temperature. The ground as an isolated layer of concrete. The vents as open into the atmosphere at ambient pressure, and the fans have been set their nominal flow rate. Finally, the pool fire, the heat release rate curve as function of time obtained in each experiment has been prescribed as an input. Well, before performing the simulations, a grid sensitivity study has been also conducted in 3 different stages. Firstly, a constant heat release rate fire of 1.3 megawatts has been modeled, refining systematically the grid, and comparing the results at the center line and the fans region, finding that the 3 final grids show more or less the same average results. Secondly, taking into account the spatial resolution needed for a proper large-scale simulation, the minimum number of cells for each fire test have been computed, finding that these 3 final grids are within this range. And finally, a real full-scale fire test conducted in the fire ATRIUM of 1.3 megawatts was also simulated with these 3 grids, finding no differences between the 2 final grids. At the end, the finest grid, in order to assure grid independency, was used. Well, once these simulations were conducted, the predictions were compared with the experimental data in 4 different regions. The temperature has been compared at the center line, ideally the plume, at the exhaust fans, and the near the walls regions. The smog layer has been also compared with experiments which have been taken into account by means of the n% method, and the makeup inlet velocities at the vents were also compared. Well, here we have the results for the first test. Above